Okay, so today we are going to start on a new topic. I am going to introduce to you the language VHDL. But before we start that, let's summarize what we had done till now. Okay, we looked at the design of digital systems, but primarily what we are talking of till now is the techniques that we have developed are useful only for designing small systems. In terms of complexity, maybe a few hundred gates. When you go for more complex systems, we require more formal methods of specifying the system, and that's one of the fundamental reasons why VHDL has evolved. There are also other languages like VHDL, but VHDL is one of the standards, and in this course we will discuss. VHDL itself is a very vast language, so when you actually study about VHDL and also learn programming in VHDL, please remember we are only going to talk about a subset of the language as far as the experimentation is concerned. Okay, and I will indicate that subset as we go ahead. Before we go ahead and look at VHDL, let's see that when we want to design digital systems, what is it that needs to be done? Okay, first of all, describing a system, we talk in terms of domains of description, and there is a very popular diagram called Gajski's Y chart. It's from a researcher called Gajski. What this shows is the looking at the description as different views of it. So you have a, let's say, a design that you want to perform. You can have a behavioral view of it. The behavioral view represents what is the functionality that you require from a circuit or from a design, primarily in terms of inputs and outputs, and that's called the behavioral domain. Once the circuit is composed in terms of components, it's then what we have is what's called the structural domain, which essentially represents the fact that you have some components and you put together, there is an interconnection of these components and so on and so forth. So that's the structural domain. There is a third view of the circuit design, which is in terms of the physical domain, which is actually including the position of the components, the position of the wires, the interconnection of the wires. So like here now, it's much more than the structure. The structure does not talk in terms of, when let's say when you draw a circuit diagram of your board, you are not really bothered about where physically, at which coordinate a particular component is located. In a physical domain, because it also could involve that how, for example, a circuit is composed of printed circuit boards, or in terms of how it is decomposed in terms of ICs, what type of connectors are used, what type of wires are used. After all, in an actual circuit or an actual system, even all these things are important. You cannot carry, if a particular wire is required to carry a lot of current, it has to be much thicker, and not all wires can all be of the same size. So even those information is important, and that's at the physical level. But when you are drawing a circuit diagram, we show with the same thickness either the power line or the interconnecting line. We don't really differentiate between the physical aspects of it. So that's the structural domain, and at the behavioral domain, we are only bothered about the input-output functionality of a system. So then what are these concentric circles? See, what happens is, these are the domains, but even in these domains, you have various levels. You need not be representing your circuit at the same level. You can have different levels, and these circles represent the various levels of representation in the same domain. For example, after all, we know that all gates, they are built up using transistors. So this could be a functionality of a circuit represented as the VI relationship, the voltage current relationship among the transistors. That's the lowest level. You can represent this circuit in terms of Boolean equations, and these Boolean equations represent the functionality of the gates in terms of the input-output relationship that, or the logic that the set of gates implements, and that is at the next level, which is the Boolean level. You can have it at the RTL level, where you are talking in terms of how you are performing every clock cycle, what transformations you are performing, and you may be writing in terms of operations and so on and so forth. This could be at a system level, where you could even talk in terms of more abstract level, where you may have components only like CPU, memory, and so on and so forth. So the functionality of the circuit could itself be described in terms of various levels. And this is what we refer to as at various points that appear in the behavioral domain. There is an equivalent structural domain. You could be talking of how many transistors are there, how they are interconnected, which base is connected to which drain, and so on and so forth. So that could be at the interconnection at the transistor level, interconnection at the gate level, interconnection at the RTL level, where you have components like adders, registers, register files, and so on and so forth, and it could be an interconnection at the system level, where you are talking of subsystems being interconnected. So you could again have various levels of description in the structural domain. At the physical domain, again, one could talk in terms of how the circuit is laid out at the lowest level, the circuit is laid out at a higher level, and so on. So that's at the physical domain. So typically, when we are talking of, in this course, we primarily deal only with behavioral and structural domain, and the VHDL also as a language only deals with these domains of description. It's not a language which is to show the geometry. It's not the language which can be used to, let's say, how the circuit layout is done. So for that, there are other languages which are used to describe a circuit at the physical level. But when you talk of behavioral and structural, when you talk of most of the tools that are, may I have silence please? Yeah, when you talk of behavioral and structural domain, look, I am talking of both in this course as well as the VHDL, the domains that it covers is only relates to behavioral and structural domain. We are not really talking of physical domain. Neither in this course nor the VHDL also is not a language used for physical domain. Of course, we will see that even among this, what is it that we confine ourselves to. Okay, so even this is a fairly large range. We are not designing circuits at the transistor level. We are only designing circuits at the gate or the RTL or higher levels. The Boolean equations, we started talking about how do we minimize Boolean equations and so on. Most of the tools that you get for design, they are represented in basically what they do is, they take a description at one level and transform it into another level. For example, when we refer to something like synthesis, it takes a description in the behavior level domain and generates a structural description. Because behavior gives what the functionality is, and once you have the structure, it essentially consists of what components it consists of, how they are interconnected, and that is the role of a synthesizer. Of course, the synthesis could start from Boolean equations like we did, for example, the K-map or the Quine-McCluskey method we designed. So that is a synthesis which is going from, in the gate level, it goes from here to here. It takes a gate Boolean description, which could be sum of products form, or it could be this, the canonical form, and finally generates a structural description in terms of, once you minimize it, then you draw the structure. You can transform it to whatever structure you want. Similarly, we will talk of, as we proceed, what VHDL we will use it for is to do the same thing at the RTL level. We will also define what RTL is. We will go from here to, in the structural domain, at the RTL level of description, where the components are not just gates, but our components could be adders, subtractors, multipliers, registers, memory files, and so on. We will come back to this once we understand what is it that we like to do with VHDL. A little bit of history of VHDL. So, United States Department of Defense initiated it in around 81, 82, a committee was formed, and then they evolved these standards, and finally the language became sort of acceptable starting mid-80s. The name itself comes from very high speed ASIC description language. So VHDL was a language which was initially designed for specifying very high speed ASICs. And let me tell you what the motivation was. It's quite interesting, and you will understand that why we require a language. Almost all defense departments, and actually many of the large manufacturers, but definitely all defense departments, would like to have multiple vendors for any component they use. You don't want to be dependent on just one single vendor to supply you a component. The reason is the vendor may have problems in production and so on, and you don't want to get bogged down by. Okay. Now, when you are talking of simple circuits and you want multiple vendors, so you design, you have a specification, and you gave the same circuit diagram to 3 or 4 people, they can all manufacture the circuit with the same specification. But when let us say it is not just, if it is not a simple circuit, it is a complex circuit, let us say you have to design something like a microprocessor. First of all, the circuits are proprietary. If let us say Intel manufactures a microprocessor, it will not like to give the circuit that it uses to anyone else, that is one thing. Second, it is not even possible to copy at the circuit level. A functionality is much more important. There is also timing relationship between signals which are important. It is not just copy a circuit diagram one for one. Any complex system, the input output, the timing relationship could be in terms of, because then let us say even when you design some simple state diagram, you have to know what is the timing relationship that it has in terms of the outputs it generates. See, even if you talk of a flip-flop, how do I describe my flip-flop? I cannot just describe a flip-flop by saying that this is a D input, this is a clock. I also have to give what the setup time is. I also have to give what the hold time is. So timing becomes important. For simple circuits like flip-flops, let us say I have to design, I can write down these timings, okay, I need minimum setup time or maximum setup time. I can talk of these specifications and give a data sheet and ask a vendor to produce. But when you talk of complex systems, it is not just simple timing relationship over a particular clock cycle, but the timing relationship over a number of clocks. How do I specify such things? A circuit diagram is maybe just one input, but it is not sufficient input. So then it has to be backed up by a huge language description. But once you start writing something in a language, the languages are so ambiguous that what one person understands may be entirely different from what the other person understands. So to be able to support multiple vendors, so that it was very clear that you require some specification which is executable. That is, two people will understand exactly the same thing within the semantics of that language, that what is it that I need to specify, what I have specified. So when a vendor delivers, it should meet that specification that is given in form of a description. And for complex systems, there are no other way but to go in for a standard description language, where the semantics are very clearly laid out, and this description language should not just be able to specify the functionality, it should also be able to specify the timing relationships. Functionality in totality, which implies the timing relationship between signals and so on. So that was the basic motivation behind developing a hardware description language. Before that, there are a lot of hardware description languages which are existing. It was not the first language, but they were existing typically in the university environments. People in the universities had developed. Industry was not having a standard language, so that was one problem. Second, they were also addressing only issues piecemeal. That is, they were good for representing a design in some domain. Like when you talk of so many domains of representation and so many levels, they were not adequate to represent. So depending upon whichever group was carrying out research in a specific area, they will have a representation for that particular domain of circuits. So there is also another objective was that it should widen the scope. The initial objective of VHDL was modeling only, because as I said before, so you only need to give a specification. So what was required was two people understand the same thing. So I modeled my design. It's not the design itself, it's a model of a design which may specify my input-output relationships and so on. And thus only a simulator was envisaged. So the tool that is required is a simulator. So if you have a VHDL description, then you simulate it, then two people should get exactly the same waveforms. You apply a waveform at the input and you look at the waveform at the output, not just the values, waveforms. You should get exactly the same waveform within the tolerances that, of course, that you want to give. So that was the initial objective. But once this language became fairly standard and acceptable, then subsequently tools were also developed for synthesizing VHDL. That is, you can go from behavioral to structural domain, or you can go from a higher level of description to a lower level of description using VHDL. So that is what we refer to as synthesis, and tools were also developed for doing synthesis with VHDL. So now let's go down, and before we start looking at VHDL, we should also understand what the requirements of such a language is, because then only we will appreciate that why the language is so vast and why there is a support required for so many things. One is the abstraction. The abstraction is related to the various levels, okay, because we said that we require to represent the design at different domains, different levels. not only in different domains but also in different levels. So there is a need to do an abstraction. The requirement of one person, if you take a complex design activity, it is not carried out by one person. Such an activity is carried out by a big team. And that particular team, at different people in that team could be looking at the design at different levels of abstraction. One doesn't need to bother about a lower level. Let's say somebody who is a system architect. Let's say how something like a processor is designed at Intel. A processor is designed with something like 20 to 50 people working on the processor. So there are people who are working only at the system level. They don't need to go and bother at, what's going to be the component or how many transistors the memory cell will require. They don't have to bother about that. So they will only look at overall what cache size. They will be doing some simulations to find out what cache sizes I should use. They will be doing simulations to find out how many instructions I should issue simultaneously. What should be the depth of pipeline. So they are looking at systems. So one should be look at that level of abstraction, and then when you refine it, you should be able to go down to lower level of abstraction. So we will see that, how VHDL does that. Modularity is very important, again from the point of view of teamwork and also from the point of view of understanding a complex design. You should be able to modularize your design and work on subsystems or components or subcomponents and so on and so forth. A very important difference between a programming language, a typical programming language is procedural or sequential execution model, where you have a set of statements. You are interested in primarily representing algorithms, and algorithms which are developed by human beings typically are developed as something like a flow diagram. You basically say that what steps need to be done, and you refine those steps, give the data structures, define the data structures, and write the corresponding algorithm. So, but because you are thinking, the human, we are sort of accustomed to thinking in terms of steps, so it primarily translates it into a sequential design. So typical high level languages were designed to represent sequential thinking, and they are essentially sequential in nature. Of course, you write in terms of steps and then you refine it. Whereas hardware is inherently concurrent. When I want to model hardware, I have to primarily think of concurrency. The reason is, if you have two components, any two components you choose, you compose, let's say you make on your breadboard you have chosen 5 gates and connected them to make a circuit. All these 5 gates are simultaneously active. They are looking at what inputs they have, and they are producing an output depending upon their functionality. It is not that at one time only, though the circuit diagram may look like this, that let's say you just make a circuit diagram with 2 gates. It's not that first you are performing an AND and then you are performing an OR. There is nothing like that. Both this AND and OR are working simultaneously. Any change here will be reflected here, any change here will be reflected here. And any change here will first reflect here and then reflect here, but that is only the data flow. The reason that, for example, if this was 1 and this became 0 to 1, and let us say this is 0, so this becomes 0 to 1, so this was 0 and this will become 1, and this was 0 and this will also become 1. The fact that this transition takes later than that, the reason is only because there is a data flow. There is a delay over here, and because of that there will be a delay here. But as such, both these components are active concurrently. Because at the time when this became 0 to 1, this, let us say, also became 0 to 1, the output will come immediately. It will not even wait for this 0 to become 1. So this is a very important thing, that all hardware is concurrent, so your language should support concurrency. Hierarchy, this is also somewhat related to modularity in the sense that we also need to build up components from subcomponents or systems from subsystems. So there is a need for representing hierarchy. You would have to partition the job and you have to build. So once the person who is designing a very high speed ALU doesn't have to really bother about anything. He or she will only bother about designing an ALU which will be able to meet a certain performance constraint. And then this ALU can be incorporated in a larger design, which could be, let us say, a CPU where ALU is just one component. So I need to be able to support such an hierarchy in terms of my design. So these are some of the main, of course, apart from all the other requirements that you typically have, these are some of the main requirements in terms of wider data type and so on and so forth. So, they are main requirements which are required for a hardware description language, and VHDL was developed with being able to support this. Okay, abstraction, I will just clarify this in the next slide. Then if you can ask this question. Modularity is being able to look at components separately. Okay, so you don't have to, you can modularize the whole thing and you don't have to look at it. The whole thing, so let us say one person who is designing at a ALU can just look at it in terms of the ALU. See, the abstraction and hierarchy and modularity, these could also be related, but they could also be separate. I will talk about this in a moment. This will clarify that. When I say here, VHDL support description of components as well as systems at various levels of abstraction. Here, let us say, let's just look at it from the point of view of timing. Okay. Depends on what is it that I am designing. Okay, I am designing, I want to match the systems at the level of delays. I can look at gate and component delays. I can be looking at, I can specify that a particular AND gate has 3 nanosecond delay and a particular flip-flop has a setup time of 5 nanoseconds and so on and so forth. So, that is one level of abstraction in terms of my timing. It is more or less the lowest level as far as VHDL is concerned. You can look, you need not bother about what the component delays are, but you can only be bothered about clock cycles. You are only matching systems at the cycle level. You don't really bother about, for example, when you do your circuit design many times in the lab, you don't really bother about what are the component delays. You only have to bother about in terms of clock cycles, how much time it will take to perform computation. So, that is another level of abstraction. Obviously, this is a higher level abstraction than that. You can also, without even bothering about any notion of delays, you can also write abstract behaviors. Okay, that is even a higher level of abstraction, where at most you might have to bother about wherever the IO is, wherever input output is, you may have to do. So, you may have to do some synchronization, for example. If there are multiple subsystems, how do they synchronize? Maybe only of importance, but the timing is not of importance. So, this is, so this is sort of different from what we call as hierarchy. Okay, it could happen that you could do a design at this level and then break it down into this and so on and so forth. So, that is a refinement process that you can do. But basically, you can look at this as different levels of abstraction, which a designer can, depending on what the requirement is, you can start the design at that level of abstraction. And it is not even necessary that each design, sometimes the design description is done only for evaluation purposes. You can do the design at a certain level of abstraction and forget about it. You may not even, you may find out that this design is actually not suitable. Even at that level, let us say at the clock cycle level, if something is not suitable, you may not go down even and design it at this level. So, there are number of, so when you go for this levels of abstraction. So, the VHDL would be able to support any of these designs at any levels. Let us illustrate what modularity is, how modularity is achieved in VHDL. Every component in this VHDL is referred to as an entity and has a clear interface. So, the modularity here, part of the modularity comes from the fact that what is the interface is very, very clearly defined in VHDL, which is very distinct from what is the body of that particular component. The body is referred to as the architecture, we will come to that. The interface is called an entity declaration. So, you declare all your inputs and outputs through what are called ports, and you declare them as whether they are input ports, output ports, what is the width of them, 1 bit, 2 bit, 4 bit, through an entity declaration. The internals of the component are referred to as the architecture declaration, which is very distinct from the interface. So, you say that, okay, this is how you will connect this particular, this component connects to the rest of the system through this input output ports, but how it, whatever is the functionality of it, how it implements the functionality, that is described in an architecture of the component. And interestingly, there can be multiple architectures at even different levels of abstraction associated with the same entity, and this is a very, very important. So every VHDL component that you need to have, there will be only one single entity, but it need not have one architecture. It could have many architectures, and at the time, of course, you instantiate this component, you have to decide which architecture you will use. These architectures could be, for example, when you talked of the levels of abstraction, if let us say you have a complex system and you want to fit the system at a cycle level with another component, then you can choose an architecture which only models that component at a cycle level. It ignores the fact that what are the delays of it. You can also have another architecture which actually contains all the delay information, and you can instantiate that particular architecture when you get the component. So you have these various levels of different architectures which can be associated with the same. We will later on take up more examples of this when we do that, but let me just try to illustrate this modularity point. A very simple VHDL description I will show for this particular component. So this is just a simple 2-input AND gate, and it has 2 inputs and 1 output, and I want to, okay, this I call AND 2, let us say, that's the name of this component. And of course, the unique thing about this is an entity. I have to define an entity for it, and I have to define an architecture. So let me underline the keywords. Okay, so in this case, so I have this entity declared, and this is the one that I referred to as the interface declaration. There will be only one entity for a particular component that you have, and this entity is declared as A and B are 2 inputs, and they are of type bit. Bit, of course, is a standard type, but you can also define your own user defined types and so on. We will see more examples of that later on. C is an out, it's a type. So these are called A, B and C in VHDL are called the ports, and these are the ports of this. So A, B are input ports and C is an output port. You can also have bidirectional ports which are in-out ports. So then, so that defines the entity of which is the interface of the AND gate. Then you have an architecture. So the architecture behavior of AND 2 is, so this particular thing relates this to the entity. For any time you declare an architecture, you have to have the whose architecture you are describing, and this is the name of the architecture. So implying that I can have different architectures, so I can have architecture behavior, architecture timing, architecture whatever. So any other name I can have for this, and that is a different architecture altogether. So I can have number of architectures associated with the same entity, and if I have a different architecture, I can have architecture timing, for example, of AND 2 is. So the name has nothing to do with it. I can choose this just a name, and it basically this is another name, so I can write a different description, and this description could also contain timing information. Timing information can be fairly complicated. For example, even for an AND gate, when both inputs, let's say one input is already 1, and when you are changing from 0 to 1, then there is a time that it takes. If both are 1 and one of them go to 0, the fall time and the rise time, and they could all be different. So depending on which level of description you are going, and you could describe, you may be able to describe all that in VHDL. So you might have to at some situation. So in this case, of course, we are describing a very simple architecture. So we are just saying C is assigned A and B. What is very important is, what are these A, B and C? Of course, in this case, once I associate an entity with it, all these ports are also visible in the architecture. But these are signals, and it's very important to realize that these signals are very different from, they give you a lot of power to the VHDL, they are very different from the notion of variables that you have in your programming languages. They tend to look like variables, like the way we have used, but there are also variables in VHDL, but they are used in a very restricted domain. We will talk about that later. But an important thing is to understand how what the signals are and what do they represent. When I say A and B, C is assigned A and B, what it implies is, basically you have to think in terms of 3 nodes in your circuit. And this is a box which is actually called the driver. So this driver for this particular signal, for this C of course in this case also happens to be a port. In my architecture I can also define more signals which are only not visible as a port, which are not visible as an interface. But all these ports are also signals which are visible within the architecture, because I have assigned this particular architecture belongs to this particular entities. So all these declarations that I made here, they are also visible here, and A and B are input signals of special type, which are ports, which are input ports. C is an output port. So I need to compute this A, B, and in this case of course it's an AND function. It's a simple function, there is nothing, and then there is a driver for C. So, but once I declare this, the implication is whenever there is any change in either A or B, automatically C will be updated. There is nothing like I have to execute it, which is different from, let us say I have in my programming language I have A and B, something similar. I execute this and then I go ahead, and now let us say I reassign A with A plus 1. Let us say in my any programming language sequential flow. So this A plus 1 is not going to change my C unless I have a loop and go back, or unless I write here again C. The model here in a programming language, the model is of a memory location. Every variable is supposed to be a memory location, does not matter whether it is in a register in the memory. And when you execute it, you update the value, but you update the value of that particular memory location or the container only at the time when you execute it. Unless you execute it again, this new value will not be reflected. But when I make this declaration, when I write this statement, it's called a concurrent assignment statement, and this is, once I have this particular architecture declared, doesn't matter any changes on A or B will automatically be reflected on C.
So what is the concept of driver you are saying?
The concept of driver is that I have this particular function which constitutes a driver, which is basically has some inputs. In this case A and B are inputs, and it executes a function, and this is a driver which drives this particular signal. The value that it generates is what is going to be assigned to the C. So this is the driving input for this. So immediately one major difference is that, for example, in case of a programming language, you can have many statements with C. I can use on the left hand side, I can make many assignments to C. In a program it does not matter, it will basically the value that is assigned last is the one that is going to be. So in this particular range, this particular C value is going to be used. In the range from this to this, in the range from this to this value will be used. In the range of following this, the last value. So whatever the last statement you executed, that's the value that's being used. But in VHDL you cannot do that. You cannot write again another statement, C is assigned A and B, and then you say C is assigned A or B. It's meaningless. Because what it means is, I have another OR gate, another driver, and I connect this to this. These two drivers are getting connected to the same. So you have to think of these as waveforms, and you don't have to think of them as storage elements. These are nodes of a circuit. That's how we have to think. There are of course ways of specifying this, but then you have to give some resolution logic. We will talk of that later on. So what implies is, let's say it's a bus. You want to form a bus. There are multiple sources to the bus. But then we know that if there are multiple sources, there may be a way of resolving the conflict. At any given time, there should be only one source. So all that has to be specified, otherwise you cannot specify just multiple. So you cannot write multiple statements where the same port or the same signal, in this case the same signal which appears on the left hand side again and again. There is no problem in appearing on the right hand side, but there is a problem in appearing on the left hand side, which is very different from the way the programming language. So this is a very fundamental difference between signals and variables, and typically you write your VHDL using signals, and they are the nodes of the system that you are designing, the circuit or the system that you are designing.
Something like C or A, after C is equal to A and B.
Yes, you can assign to something else. You can assign, for example, you can have this statement A and B, then you can have D is assigned C or A. Okay, now if you do that, okay, in this case you cannot do, because not in the architecture, because this is an output port. Okay, but let's say if I in my architecture, let me define something else. I can do this. Okay, so where D is a signal which is an internal signal, I can define C signal D bit. I can do this. D is an internal signal. So what now this is going to define what? This is going to define A, B, D, a circuit like this. A very important thing about this is it doesn't matter in which order you write. I can write this earlier and I can write this statement. So just because of the fact that this is at the out, this you are assigning, and here this happens to be on the right hand side and this happens to be on the left hand side. Whereas in case of a variable, it will be meaningless to write this first, because D will not even have a value that is assigned to it. Before assigning a value, I cannot write, if all of them are variables in a programming language, I cannot write this. But in VHDL, when I am doing concurrent assignments, these are concurrent assignments, I can write this in any order I want. Because what it implies is, just like I drawing the circuit, I can draw the circuit in any order I want, and it will not really affect the functionality of the circuit just because I drew the OR gate first or AND gate. Because what it is going to do is going to take the AND of these two and put here. Whenever any value changes over here, it will take the OR. Doesn't matter whether the value changes over here or. So you can write this statement first and this statement later on.
So can we assign C equals to C and D? Is that
no, you cannot do that. You cannot write, that's the same notion. So you cannot, then you have two drivers now. Okay, so there is a feedback. So there are methods of, we will see, of course, what happens is in case of VHDL, so this I am talking of purely concurrent behavior. The VHDL also allows you for some sequential behavior. The reason is very simple, because when you want to represent complex algorithms, it's very difficult to write it in terms of this concurrent. You are not going to break it down into just concurrent statements. An algorithm you want to encode, let's say you want to implement the GCD. It's very simple to think of the GCD in terms of sequential computation. So VHDL also allows you to do that, but in a very limited sense, and we will see that in a restricted sense how it does that as we go ahead. So this is, let's talk of the concurrency. The concurrency basically comes in VHDL by looking at what are called processes. So every VHDL complex description consists of number of processes. And these processes are primarily non-terminating. That is, what happens is this: once you have 1, 2, whatever, n processes, all these n processes are acting concurrently. The way the sequence, if you want to write procedural descriptions, within the process, it is sequential. So it allows you to mix the two. So the descriptions that you write within the process are executed sequentially. There also we will see that. And outside, so what you have is all these processes communicate with each other only through signals. And these signals, as we said, basically you can look them as waveforms. So they are nodes of the circuit, and so basically you can say that they are connected to each other through some nodes, circuit nodes. So they talk to each other only through signals. Processes themselves are sequentially executed, but once the process is finished, it goes back and starts executing again. The number of things that are allowed within the process, because a lot of the time as far as this course is concerned, we will be talking of process descriptions, because that's what is important to us for designing systems. So we will talk of that. If you relate to what I wrote before, this is one single process and this is another single process. I have not written, so there are two ways of writing a process. Once you can write it using the syntax the VHDL provides, saying process, where you say the process begins, give the name of the process and so on, and then you say the end process has ended within the body. But a concurrent assignment written without anything else is also a process by itself. So it is like one process, there is like another process. So if any of the concurrent, let's say you write 5 concurrent assignments, they are like 5 processes. And they are all active. The implication is this particular statement is being executed repeatedly, this particular statement is being executed. And they never terminate. So and what are they communicating? In this case, they will communicate through the shared signals. The shared signals are D. So the output of D is an input to this particular process, and they will be communicating in this manner. Things like variables, later on we will see more examples of this. Variables are allowed within the process, only within the process. Variables cannot be written outside the process. So when we write the process descriptions, we will see that you can write a complete algorithm. The code inside the process could be very similar to the way you write in your C or Pascal or any high level language. Very similar, some small syntactic changes. So you can use variables and so on and so forth. But finally, both at the inputs as well as at the outputs, because you can only communicate through signals, so you have to assign these variables to signals, or you have to copy those signals onto variables, and then you can start the computation. Whatever algorithms that you write. But once it finishes, then it again gets back, and we will later on study a little bit more about this process. So the concurrency essentially comes from the model that you have either these processes, or as I said, every concurrent assignment is also a process, multiple of these processes which are active together. Okay, I will clarify this with some examples in the next class. So let me just go through this, because I want to finish up to a certain level. Processes are concurrent, sequential activity within each process. This is the point that I was trying to make, that any sequential activity is, so otherwise processes are all concurrent. There are also nesting of statements possible. So this nesting also in some ways gives you, both supports concurrency and modularity also. So you have concurrent statements in a concurrent statement. So if they have more concurrent statements within a concurrent statement, they are all concurrent. So they all, concurrency is flat in the sense that basically all processes are active all the time. So there is nothing like it starts and it ends. Sequential statements in a concurrent statement. So within a process you can have sequential statements, and sequential statements in a sequential statement. You cannot have within a sequential statement, you cannot have any concurrent statement. So that's very clear, because that's meaningless. So you have basically processes which are all concurrent, and within that you can have sequential statements. And that also defines what type of an hierarchy that VHDL supports. Let me what I have written as C is all concurrent, and what I have written as S is all sequential. So any description, first of all you have to take a description and then divide it into concurrent parts. When you describe it as concurrent parts. Then within, so each of the concurrent parts itself could consist of other concurrent parts. And this is only, like for example, this is only for hierarchy. Essentially, you could have moved C4 and C5 right up to this level. It doesn't matter because they are all concurrently active. So this is a process which is, so this is something which is active all the time. This is also active all the time. This is only a composition of these two to get that. Similarly, these two, composition from that. And once you are within this, within concurrency, you can write a set of sequential statements. And once you write sequential statements, it's clear that how, so when it comes to C7, C7 is nothing but execution of these statements and then you go back and execute it again. So these are not concurrent statements, they are sequential. Similarly, you execute S3, then S4, S4 itself consists of S13 and S14. And so you execute this in this sequence, you execute this, and then you get back to that. So you can, that is how you can break down your complex design into descriptions which are lower level. Okay, so that's what we do. Okay, we'll stop over here, we'll continue. Yes.